Assalamualaikum and good to everyone. Today we are going to present on the topic of types of condenser, specifically direct contact condenser and surface condenser. Before that, this is our group members. The first one is Atila, Yosewe, me, Haikal Mokhtar, next Nurdiana, and the last one is Fazri. Our presentation will cover the principles, advantage, disadvantage, and practical example related to this type of condenser. Let's get started. Okay, before diving into the specific of each condenser types, let's first understand what a condenser is. A condenser is a key component in thermal power plants responsible for converting steam back into liquid water by removing heat. This process plays a crucial role in maintaining low pressure at the turbine exhaust, which increases the efficiency of the Rankine cycles. In today's presentation, we will focus on two types of condenser. The first one, the direct contact condenser. The second one is the surface condenser. Okay, what is a condenser? A condenser is a device that condenses steam into liquid by removing heat. It helps in maintaining the overall efficiency of the power plant cycle. By cooling down the steam and turning it back into water, condenser enables the recirculation of water in the system, reducing water consumption and improving energy efficiency. The condenser is then returned to the boiler for reuse and ensuring sustainable operations. Okay, now let's look at the two main types of condenser we'll be focusing on in this presentation. The first one is direct contact condenser. In this type, steam and cooling water are in direct contact with each other. The second one is surface condenser. In this type, the steam is cooled indirectly through a heat exchanger where the steam never comes into direct contact with the cooling water.
Okay, I will continue for the first type, which is direct contact condenser. What is direct contact condenser? Direct contact condenser is the exhaust steam and cooling water come in direct and mix together. Steam condense, suddenly achieving the temperature of the cooling water. Condensate and cooling water are continuously taken out. For the advantages and disadvantages for direct contact condenser, first advantages is less water quantity required. Construction is simpler, less costly, required small for space, and next is for disadvantages is if condensate contain impurities cannot be reused. Then low vacuum efficiency, not suitable for large plant, and more power required for air pump. Next, there are three types of direct contact condenser. First is spray condenser, barometric condenser, jet condenser. So I will explain first about spray condenser. First, the cooling water is sprayed into the steam to condense it into saturated water. And a part of the condensate, which is state 4, is reused as the feed water. The rest is cooled in the dry cooling tower, which is state 5. High purity water is necessary because cooling water mixed with the steam, and the flow of the water is significantly higher than the steam flow. Next, for the explanation for the barometric condenser, the cooling water pass through buffer, increasing the surface area. Steam entered from below and condensed on contact. The mixture is directed to the hot wheel through the tailpipe, and the tailpipe is compressed the mixture to the atmospheric pressure. The wider pipe reduce friction, but make the system larger and heavier. For last is jet condenser. A diffuser replaces a tailpipe, lowering high and increasing pressure more efficiently. Diffuser are more compact compared to the tailpipe. So at the right figure, there's the schematic flow diagram for direct contact spray condenser, schematic diagram for direct contact condenser barometric, and the schematic for the jet condenser. Next slide. I will explain the advantages and disadvantages for each direct contact condenser, which is for the first spray condenser. The advantages is simple design and low cost, but the advantages is required clean water. It is suitable for small power plant, and for barometric condenser, the advantages is handle vacuum condition, and the disadvantages is the high installation height, and it is suitable for industrial vacuum system. Lastly, for the jet condenser, the advantages is the compact design, but the disadvantages is the higher water usage, and it is suitable for the process industry and the power plant.
So we look at the first on spray condenser. This is our example. For the data, we need to find circulating water flow rate for M.5. So this is step by step for this solution for spray condenser. We look at the step 1, refer to the energy balance equation. So we look at the step 2, we need substitute the amount from the data, and then for step 3 we can solve for M.5. So the answer is 46.98 kilojoule per second. That's the water flow rate M.5. So next, we look at the barometric condenser. For this data, for this example for barometric condenser, we need to find the pressure drop due to friction. So this is solution step by step for barometric condenser. We look at the step 1 using the governing equation. Pressure atmosphere minus pressure condenser plus pressure drop due to friction equal density times gravity times height. The step 2, we need to rearrange to find pressure drop due to friction. The last formula, we get the pressure drop due to friction equal density times gravity times H minus bracket J atmosphere minus pressure condenser. Step 3, just substitute the values from the data. So the final answer, the pressure drop due to friction is equal 9872.9 Pascal. So this is the solution for barometric condenser. And next, we look at the last type of the direct contact condenser, that's jet condenser. The data, this example of the jet condenser, we need to find the condensation efficiency, and is all the steam is condenser. Is the solution for jet condenser. We need to look at the step by step. For the step 1, we use the energy balance equation. That means Q steam equal to Q water. The step 2, we need to calculate heat absorbed by the cooling water. So for cooling water is equal to M dot mass flow rate water times Cp times bracket different temperature out minus temperature in. So the final answer for heat water, we get the 2090 kJ per second. Step 3, we need to calculate the heat released by steam. So the formula is Q steam equal to mass flow rate steam time enthalpy steam. Value of Q steam, we get the 12,500 kJ per second. Step, we need to check if all steam is condenser. So we need to compare Q steam and Q water. So the Q water we get is 2090 kJ per second, is less than over Q steam equal to 12,500 kJ per second. So since Q water is much less than over Q steam, so not all steam is condenser. So that's all from me. Thank you.
So today I will present about the surface condenser. So the surface condenser is a shell and tube heat exchanger, and there is no direct contact between the steam and cooling water. Thus, the cooling process will be done on the surface of the tubes. So for the coolant parts, even the impure water can be used as a coolant. So the requirement for the coolant is not really important. So it's mostly used in the power plant, but it has a high computer cost and it needs huge space to install. But the good thing is it will provide a good energy saving and efficiency. So from the study, a single pass has a greater overall plant efficiency and it will reduce the thermal pollution, but it needs twice the water flow and form of the pumping power as compared to the two-pass surface condenser. So, as mentioned, there are some classification of surface condenser, which the first one is the downflow type, which the steam will enter at the tops and flow downwards. So the water flowing through the tubes in one direction, lower half come out in the opposite direction in the upper half. So the second one is the central flow of the condenser. So in this condenser, the steam passage are all around the periphery of the shell, and then the air is passed away from the center of the condenser, and then the condensate will move radially towards the center of the tube nets. So some of the exhaust steams will moving towards the center and meets the undercooled condensate and preheat it. Thus, it will reduce the undercooling. So the last one is the evaporation of condenser. In this condenser, the steam to be condensed is passed through a series of tubes and the cooling water falls over this tube in the form of spray. So a stream of air flow over the tubes will increase the evaporation of cooling water, which will further increase the condensation of the steam. Next, this is the requirement of the modern surface condenser. So the first requirement is the steam entering the condenser should be evenly distributed over the whole cooling surface of the condenser vessel with minimum pressure loss. So the second one is the amount of cooling water being circulated in the condenser should be so regulated that the temperature of the cooling water leaving the condenser is equivalent to the saturation temperature of the steam corresponding to steam pressure in the condenser. So the third one is the deposition of dirt on the outer surface of tube should be prevented. So the last one is there should be no air leakage into the condenser because the presence of air will destroy the vacuum in the condenser and thus it will reduce the work of 10 per kg of steam. So if there is leakage of air into the condenser, air an air extraction pump should be used to remove air as rapidly as possible. When it comes to the advantages and the disadvantages of the surface condenser, so there are few advantages for the surface condenser, which is even the pure impure water can be used as a coolant, and it will provide a good energy saving and efficiency. So the disadvantages is it needs a high capital cost and it needs a huge space to install the surface condenser.
Okay, I will present about the example and solution about the question surface condenser. There's the for question. A is the maximum allowable exit temperature of cooling water. It's mean that TW2, and the question B is total heat transfer. It's mean that Q, and question C is condenser vacuum pressure when vacuum efficiency need is 85%, and we call it with P. And question D is quality of steam at condenser inlet. We call it with X. The first question is maximum allowable exit temperature is TW2. We get it from the efficiency condenser formula is delta T actual divided by delta T max. The delta T actual is TW2 minus TW1 and divided by T saturation at minus TW1. And we know the TW1 and we know the T saturation. So we get the TW2 is 38.2 degrees Celsius. And the question B is a total heat transfer of a Q. For searching the total heat transfer, we have to know about the coefficient of water, 4.182 kilojoule per kg, and we have to know about the M.W, that 40,000 kilogram per hour. It's from the question, and we transform it to kilogram per second. We got the 11.11 kg per second. So the formula about the total heat transfer or Q is equal to M.W times coefficient of water times delta T, and we get the value of Q is 752.684 kilowatt. Okay, the third question is the condenser vacuum pressure, and in this solution we call the condenser vacuum pressure with a variable P. And the first, we have to know about the absolute pressure inside, with the formulation is the pressure barometer reading minus by P, and we get the value, but there's the variable inside that value. And the second is we have to know about the P saturation at 40 degrees Celsius, and we get this from the table. And the next is we have to know about the partial pressure. Partial pressure is absolute pressure inside minus by the phase saturation at 40 degrees Celsius, and we get a value, but there's the variable P inside. And the next is we have to know about the mass of air present. The formulation is partial pressure times V divided by R. R is the constanta, and the T is 40 degrees Celsius, but we transform it to Kelvin, and we get the value of mass of air present, but there's the variable P inside that we have to search the P. And the last is we calculate from the vacuum efficiency formulation. The vacuum efficiency formulation is actual vacuum divided by ideal vacuum. We know that the vacuum efficiency is 85%, and the actual vacuum is P. The actual vacuum is P is we have to search, and ideal vacuum is a barometer reading pressure minus by the mass of air present, but on cmHg. So we can get the P. The value of P is 74.26 cmHg. Okay, the last question is quality of steam at condenser inlet, or X. For such the X, we have to know about the enthalpy at 40 degrees Celsius. We got it from the table, and coefficient of water, and m.s. And we transfer m.s from the kg per minute from the question into kg per second. The next, we input the value of H variable on the energy balance equation, like on the slide. And we have to know at the right side m.w times Cp times delta T is a heat transfer. We get it from the question B. And the left side, we know each value of each variable except the X. So we get the calculation of X with submitting the value from the before question and from the known information. And we got X at 0.61335. Thank you.
Okay, this is our conclusions. Condensers are essential in power plants, especially in the Rankine cycle, as they turn steam into water, maintaining low turbine pressure, and improve efficiency. There are two main types. The first one is direct contact condenser, where steam mix with cooling water. For the surface condensers, which keep them spread using a tubes. Direct contact types are simpler, but need high purity water, while surface condenser are more efficient and prevent contamination. Both play a vital role in enhancing thermal efficiency, reducing pollutions, and supporting sustainable energy. Proper maintenance ensures they perform effectively. Thank you. This is our presentation. Hope you enjoy.